Hello everyone. Okay, welcome to the mechanics of materials. And in this video, we are going to go to a new section called simplification of force and couple system. And before that, I just want to introduce a very small, very little section from very little of the detail of the moment calculation. Yeah, because this relate to the further simplification of the force and couple system. So I put this section. So I put this section in this video. It's called principle of moments. Actually, it's very easy. The principle of moment is just tell you, okay, we can we because we have say that the moment in 3D case moment is equal to position vector cross the force vectors, but sometimes we can decompose the force because we decompose the force. Okay, force can do a decomposition. Yeah, because of the force vector add the other force vector become a resultant force vector. But in the reverse, force can decomposition in the two force vectors. Okay, and in sometimes when you do the force decomposition, will make the calculation easier. Okay, yeah, there's just example. For example, this is a position vector r and force vector is here. The force acting on this point, we want to calculate the moment caused by the force with respect to the point O. Okay, r cross F. And but we can also decompose the force, use the parallelogram to decompose the force to F1 and F2, and the moment is just equal to the moment caused by the force 1 plus the moment caused by the force 2. Okay, very simple concept. Okay, we can decompose the force and doing the moment calculation. Okay, because sometimes they will make the life easier. Okay. Okay, so and here is some example for this problem. And I don't want to mention too many detail for these simple questions. Okay, just the decompose. It just let you practice to decompose the force, and then calculate the moment. For example, in this problem, force is 5 kilonewton. Okay, and I want to calculate the moment caused by the force and with respect to the point O. Okay, and then yeah, in a 2D case, we just find a level arm. The force is here. Okay, the force here and reference point is here. So we draw a line of action here. We draw a line of action. Yeah, which maybe is a little explanation will be good. Okay, we draw a line of action here because the force vector is here. This line of action, and we make a find a perpendicular distance between the reference point, perpendicular distance between the reference point and the line of action of force. So the magnitude of force times the lever arm. That's the moment. Okay. But we can, yeah, in this problem, just say, okay, we have another way. We can decompose the force. We can decompose the force here, and it's a fx force times cosine 45 degree. Here is force times sine 45 degree. We decompose the force. Okay, and this force line of action is here, so the lever arm will be here. Okay, and this force is pointing downward. Maybe I use another color. Okay, this force is pointing downward, and the reference point here. So reference point here. So reference point here. So this is a lever arm. Okay, lever arm. This also this and this also lever arm. Okay, so this force labor arm is here. He says sine and 3 times sine 30 degree, and this force here 5 times sine 45 degree. The labor arm is here. Okay, this is just equal to, because it gives you the this is length. The length here I think is 3. So in 3, okay, 3, yeah, it's 3 cosine 30 degree. Okay, unit m. Okay, yeah, just decompose the force and find the lever arm. Okay, that's all. That's all. This that's called principle of moment. You just can decompose the force. Okay, you can decompose the force and sum of all the moment caused by this decomposed force, and you will have the same answers. Okay, so it's very easy question. I don't want to address this any further, and I will update the answer for this slide. Okay, and there are some very easy practice for you. Okay, so after the principle of moment, okay, so we are going to the next section. It's called simplification of force and couple system, and this is very we are getting into the core material, the core of the mechanics of material course. And before I just introduce the calculation of force, position factors, and the moment. Okay, that's the very basic for you guys to warm up. Okay, here we gradually touch the core of this course. And first of all, we just introduce a concept called simplification of force or couple system. And in the mechanics of materials, I said that before, what the goal of this, the essential content for this course is we want to calculate the force, the internal force when we apply external force to a material. Okay, when we apply we apply external force on the material or on a member. Okay, and what's the internal force will be. Okay, that's the core of this of this. That's the core of this course. Okay, so and sometimes when we not only act only one force on the material, sometimes most of the time we will act lots of force on the material or on a member. Okay, and when this situation most of the time we want to do the simplification of the system. Okay, because that will make life easier. Okay, for example, this member or this material, well, we apply a lot of external forces and want to make a simplification. Okay, the simplification is we only have one resulting force and acting to a certain distance with respect to the reference point. Okay, and okay, this is just concept. Okay, how to do that? Okay, how to do the simplification? So before simplification and after simplification, your resulting force must be the same, and your resulting moment before simplification and after simplification they also must be the same. Okay, this is the way we do the simplification calculation. Okay, so because the before simplification, after simplification, the resulting force and resultant moment are the same. So there is a terminology called equivalent system. Okay, so we can say if you satisfy these two conditions, we can say you create equivalent system after the simplification. Okay, and this technique we will use a lot during in the whole semester. Okay, and okay, you just you can look at the other text and yeah, external is the I think the most important thing is the first point. Okay, the other two is for your reference. Okay, the most important is the first sentence. Okay, before and after the resultant force and resultant moment must be the same. Okay, so okay, let's raise one example in this problem. Okay, this is a very typical problem in this course. So there is a beam here, Okay, there's a beam, and we'll apply a external force and moment on the beam. Okay, and right now we just want to know we just want to do a simplification of the system. And after simplification, we only had one resultant force here. And what's the resultant force? And also, where is the resultant force acting? Okay, so this D is we are going to calculate, and D is the distance between the acting point of the force and the reference point. Okay, yep. Yeah, that just like say, like I said, just like just like this scheme, just like this scheme, we had applied a lot of force, and after simplification, we only have one resultant force, and we also want to know where is this resultant force, where is this resultant force acting? Okay. Okay, how to do that? Just like this, that's just what I say, what I write right here. Okay, before and after your resultant force and resultant moment must be the same. Okay, so let's start with example 3.17. Okay, so let's first of all we just calculate the resultant force and resultant moment before simplification. Okay, let's change the color. Okay, let's say, this color is not this bad. Oh, so sorry, I chose the wrong one. Okay. Okay, so let's say before simplification. Okay, what's the resultant force before simplification? And with some looks like it's 2D system. So okay, resultant force. We have X component. Okay, so let's say the first one is this. There's a force here is 4 kilonewton downward. Okay, looks like there is no X component. So okay, no, and so okay, very good. And the other force, 8 kilonewton here. Okay, and then we can decompose this force to X component and Y component. Okay, so the X component, okay, it give you the information of slope. Okay, maybe the word is the word character is too small. Okay, give you the information of the slope. Okay, so 8 kilonewton apply here. So the X component is 8 kilonewton times 3/5. Okay, okay, X component. So let's say 8. Okay, times 3/5. Okay, and anything else? X component. We check anything else on. Do there any force contribute the X component of force? No, so it's 4.8. Okay, kilonewton. Okay, so what's the resultant of the force before the simplification? Okay, so here is 4 kilonewton and point down. Okay, and the convention. Okay, there is a convention issue here for the upward and right is positive, and downward and point to the left is negative. Okay, so in y this is point down, so it's -4. Okay, and here is the 8 kilonewton. I think we have Y component here. So Y component is point up, so it's plus 8 times 4/5. So what's the result? So this is 6.4, so it's 2.4 kilonewton. Okay, because like I said, for the equivalent system, before simplification and after simplification, the resultant force must be the same. So we find a resultant force X component and Y component before simplification. So that also means after simplification, the X component is also 4.8 kilonewton and Y component also 2.4 kilonewton. That's why this picture draws a picture here, 4.8 to the right and 2.4 to the up. Okay, and don't forget it's the unit of force is kilonewton. Okay, because we use kilonewton here. Yeah, so it means the unit is kilonewton. Okay, so we'll find a resultant force after simplification. And next problem is where is the force? Where is the resulting force acting? Okay, and acting we measure from point O. So there must be a reference point. Be careful. There must be a reference point. Okay. So the reference point is okay. So when we want to determine the position of the resulting force, we need using the moment. Okay, let's see. Okay, let's do the same thing. Before simplification. Okay, before. Okay, what's the moment? Okay, before what's the moment? Okay, and the moment is with respect to the point O. Okay. Okay, so let's start with it. And looks like it's 2D system. We just use the scalar formula of the moment. We don't use the vector formula for the moment. Okay, because if we use the vector formula for the moment, this will make this problem so complicated. In such 2D problem, we only need to use the scalar formula of the moment. Okay. Okay. First of all, the force is 0.4 kilonewton point down. Okay, and the reference point is here. So in the scalar formula of the moment, we just only need to know the magnitude of force and the lever arm. And lever is so it's line of action of force. So this will be your lever arm. It's 4.5. So it's 4 times 1.5. 4 times 1.5. And the reference point is here. So this force will cause the rotation like this. This will cause the rotation clockwise. Okay. And also sign convention, clockwise and counterclockwise. Clockwise is negative, counterclockwise is positive. Okay, so this will, because reference point is here, so this will generate a clockwise rotation. So there will be a negative here. Okay, it's clockwise, so there's a negative. Be careful. Okay. And here, this shows the 15 kilonewton times meter. So it means a moment. Okay, moment. Okay, Newton times meter is moment. So it's it shows here 15 kilonewton times meter, and this direction looks like the moment is also clockwise. I think it's also clockwise. So clockwise is minus. So it's minus 15. And okay, so let's look at here. So this force, like I say, in this problem, I think just like I say, sometimes when we come to a moment, it's better to decompose the force. Okay, when you decompose the force, it will life easier. For this is such kind of problem. Okay. If we decompose in a x component, y component, it will make the calculation moment easy. Okay, here. Okay, this will decompose 8 kilonewton decompose. This will be okay. Let's see. This is let me see. So this is 4.8. This and here is 6.4. Okay, let me check. Sorry. It's reverse. It's reverse. X is 4.8. X is 4.8. Y is 6.4. Okay. So okay, let's see. Okay, for this force 6.4 kilonewton. Okay, and reference point here. So let's draw a line of action is here. Line of action is here, and I think this will the reference point here. So this will give you a lever arm is here. So the lever arm is 1.5 plus 1.5 plus 1.5. So it's 4.5. And since it's 4.5, so it's 6.4 times 4.5. Okay, because reference points here and this force is upward, so it will cause. Okay, this is counterclockwise, right? It will create counterclockwise, and counterclockwise is positive. Okay, and the force for this 4.8 kilonewton, this force also generate the moment. Okay, be careful because it's give you here. It's give you the information of this. This force is 0.5 meter higher than the reference plane. Okay, so this force will also cause the moment. And also, okay, and its force magnitude is 4.8. And what is the lever arm? Okay, we draw a line of action here. This is a line of action here for this force, 4.8 kilonewton. And the reference point is here. Also, this is your lever arm. And lever arm is 0.5 newton. 0.5 meter. So here is 0.5. And okay, next thing is clockwise or counterclockwise, because reference point O is here, so the force here will generate, okay, looks like it's clockwise. Yeah, think about yourself. This will generate a clockwise moment, and if it's clockwise, it's negative. Okay, so that's all the moment we have. Ooh, let's see if I get the right answer. Okay, so minus 6, minus 15. Okay, plus 6.4 times 4.5 minus 4.5 times 0.4.8 times 0.5. Okay, so it's 5.4. Okay. Okay, the before simplification, the resultant moment is 5.4 is kilonewton times meter. Okay, so this result. This is the moment before simplification. Okay, and let's see before and after simplification, the total the resultant moment must be the same. So let's see. Okay, after the simplification, we have one resultant force, right? We just calculate, and the x component is 4.8, y component is 2.4. Okay, and okay, and the reference point is here, so we only this force create a moment. Okay, this force won't create a moment because the labor arm is 0. Okay, think about yourself. Think this point by yourself. The force of this force doesn't create a moment because labor arm is 0. Okay, so after the simplification, we also have a moment. Okay, and it's caused by the FRY. Okay, and times the distance D. We just don't know. Okay, we just don't assume it's D. Okay, and here it's this force we see here is going to up, so it will create a counterclockwise. So it will be a positive. So maybe I should write here negative, okay, positive, negative. Okay, so this counterclockwise. Okay, so counterclockwise, so it's already, so it's positive. So, okay, so this is good. And okay, the resultant moment before simplification is 5.4 kilonewton. Okay, so FYY we already know is 2.4, and times D equal to 5.4. So D will be, what's the answer? D will be 2.25, right? D will be 2.25. Unit is meter. Really? Let me check. 5.4 divided by 2.4. Okay, 2.25. Okay, 2.25 meter. Okay, so that's a very typical problem for the force, the simplification of a force on couple system. Okay, just use the concept. Okay, we want to create equivalent system. Okay, in the equivalent system, the resulting force before and after simplification must be the same, and the resultant moment before and after simplification must be the same as well. Okay, using these two concepts, you can create an equivalent system. Okay, and it's a very important skill in the materials and mechanical materials calculations. Okay, and next video I will show you another kind of more difficult example, but actually not difficult. It just become like a 3D problem. Okay, so that will make you do a lot more brainstorm. Okay, so I just stop the video here. Okay, and see you in next video. Okay, bye. Oh.